So here we start our second part of this topic on problem solving in quantum physics of atoms. And this is question 5 with us. Scientists observing the absorption spectra from a distant galaxy hypothesized a hydrogen-like atom with the spectral lines matching those of terrestrial hydrogen. But this hydrogen was different, and in what way? Let us see. In this unique atom, the electrostatic interaction was replaced by gravitational interaction. In a hydrogen atom, you have the electron and the proton interacting with each other with electrostatic forces or electrostatic potential. That has been replaced in this unique hydrogen-like system by gravitational interaction. So both the species are electrically neutral, but for the sake of convenience, we still call them E and P. E and P don't stand for electron and proton. We just call them E as the particle which goes around, the lighter particle, and P the heavier particle which is at the center, which interact with each other based on gravitation. Now the question says the two electrically neutral interacting species called E and P had masses F times the masses of electron and proton respectively. So once again we have a heavier particle in the center, a lighter particle around it. Based on this and the fact that the spectral line is identical, even though the interaction is much weaker on that length scale, find what should be F, given that the mass of electron and mass of proton are as provided. Let's proceed with the solution of this problem. To solve this problem, we need to first note that what does it mean by hydrogen-like? Why are we saying this is hydrogen like? Right? Both the interactions, the electrostatic interaction as well as gravitational interaction, the forces go as 1 upon r square. The nature of forces is identical, and therefore the symmetry of the potential is identical. Whether you have the gravitational problem or you have the Coulomb problem. Because this symmetry is identical, your solutions of the hydrogen atom are also identical. The hydrogen-like atom, which is based on gravitation. So it has identical solutions, but which differ by certain constant values, because the expressions for gravitation and the expression for Coulomb interaction, they both differ by some constant values. So let us apply this difference and see what we get. You have the expression for radiation associated with the longest wavelength of the Lyman spectral series of hydrogen. So I would write for that the general expression where NF and NI are subscripts identifying the final state and the initial state associated with the transition, is equal to the Rydberg constant with let me help you see this part. I shall write this again at the bottom. I hope that is fine. So the difference between the gravitational interaction and the electrostatic interaction would essentially lie over here in the Rydberg constant. We will still get energy levels going as something upon some number upon n square for this system which has gravitational interaction, because I mentioned that the force still goes as 1 upon r square. So the form of the force is same, so the spacing between the energy levels is same, and a similar expression would also hold if the interaction was gravitational in nature, but the constants which are sitting in the Rydberg constant would be different. And how different would they be? Let's have a look. R for your hydrogen atom is given by W upon Hc, where En is minus W upon n square, or minus 13.6 eV upon n square. W has the expression as Me e to the power 4 upon 8 times epsilon naught square, the permittivity square, times the square of the Planck constant. And this is how we get the 13.6 eV. So when we have gravitational interaction, how do we modify this W, or effectively, how do we modify this R? Whatever I have written here is for the electrostatic interaction, which is your hydrogen atom. This is not the hydrogen atom that the question states they discovered hydrogen-like atom. We'll come to that in the next slide. So your electrostatic interaction with all your constant terms would look like E square upon 4 pi epsilon naught r square, E square upon 4 pi epsilon naught r square, and that is replaced by G m1 m2 upon r square. This part is common, and if you look at e to the power 4 upon epsilon naught square, this is the term that appears in R in the value of the Rydberg constant. When comparing these two expressions which are written at the top, I would say that it should be replaced by 4 pi square G square m1 square m2 square. If I make this replacement, I would get the correct Rydberg constant of my system. So W becomes mass of the electron times G square times mass of the electron square, mass of the proton square, and then you have this 4 pi the whole square divided by 8h square. And from there, I can write the Rydberg constant as W upon Hc. Now I can call this W tilde to distinguish it from the ionization potential of the hydrogen atom, because this is a hydrogen-like atom with gravitational interaction. So I've added a tilde over here to distinguish this from the pure hydrogen atom, which is based on electrostatic interaction. Let's go to the next slide. You may wonder, is there a direct way of getting this expression? I have just compared the two forces and said this is how their terms are different, and that's how I wrote down the W tilde or R tilde. But if there is a direct way, what we would do is the following. We would compare, in this case, the centripetal force with the gravitational force. Because that is what is keeping the atom stable. There is an attractive force, and then there is a force which is sending it out. When you compare this, you have another expression, which is your Bohr's quantization condition. And so these are the two expressions which are available with me. I can solve the first one, and I will arrive at, from 1 I will get V is equal to 2 pi g mass of electron, mass of proton divided by NH. And further I can get the R to be NH bar upon MV, but here it's mass of electron. There are two masses times V, and this will give me NH bar into NH bar upon ME G ME MP. You will note that this part of the expression has been used over here, and the result for the velocity has been used over here. So what does it tell for R? R is N square H bar square upon G ME square times mass of proton. That brings us nearly to the end of this calculation. Let us write down the expression for U. So U, which is the potential energy under gravitation, will be G m of electron mass of proton upon R, the gravitational potential. The kinetic part will be minus half of U, and your total energy will be, which is E is K plus U, and that will be minus G mass of electron mass of proton upon 2 times R. We have found the value of R in the previous slide, and let us plug that in here to obtain that your total energy is minus G square mass of electron cube mass of proton square upon 2 H bar square. And the important thing here is N square. That tells us that the dependence of the energy levels with the quantum number is just the same. And here I will write down the expression for the wavelength radiated by this atom, and that will be given by omega tilde upon HC into 1 upon N final square minus 1 upon N initial square. And this system is quite similar to the hydrogen atom, except the difference sits over here, And another important thing to note, it is given in the question that the masses of these particles which have no charge are in the same ratio but much higher, and higher by a factor f. Now, if each of this mass of the E particle and the P particle are f times higher, then the total mass would be higher by f raised to power 5, and this is the factor that would sit inside omega tilde, W tilde. Going to the next slide, we can write lambda of the hydrogen atom divided by lambda of this new atom is in the ratio of W tilde upon W, and this will give us G square ME cube MP square F raised to power 5 upon 13.6 eV. And all the constant values are given to us, so we can plug them in and obtain the answer as 0.2 into 10 raised to minus 78 and F raised to power 5. But then it's given that the wavelength of the transitions are actually the same, that even the system where the fundamental particles had no charge and they only interacted with gravitation, they emitted the same radiation. So this is equal to 1. And from here it follows that F is 5 times 10 to the 77 raised to power 1 upon 5, or the masses are in the ratio of 3.4 into 10 to the power 15, which completes the problem. And this shows that the gravitational interaction is extremely weak, though it has the same symmetry and it would lead to the same kind of structure in terms of the spacing of the levels if such a system could have existed. It's only a hypothetical system, but then to get a comparable wavelength of transitions or to get a comparable spacing between the levels, the masses should be extremely large, and at the same time they should be confined to a very small space. So the mass of the electron and the mass of the proton should be heavier by so much amount. That's a huge amount. Let's go to the next problem. Question 6 asks a different question. What is the percentage error in the estimate of the frequency of the first Balmer line if the proton is taken to be fixed at the origin instead of having a motion about the electron-proton center of mass? Now, it's a two-body system, so you would expect that not only the electron goes around, but there is certain motion associated for the proton as well. So this is what you expect for a two-body system. But the mass of proton is much larger than mass of electron. So for most purposes, you can just neglect this small motion. On the other hand, there will be some error when we do this neglect this motion, and this question asks us to find what kind of error would be there in the frequency value of the first Balmer line. So the frequency of the Balmer line, lambda Balmer line, is 2, and the first Balmer line is given by the final state 3 is equal to the Rydberg constant and 1 upon 2 square minus 1 upon 3 square. And my error will sit in R because R is given by mass of the electron times electron to the power charge to the power 4, 8 times epsilon naught square C H cube. and my error is sitting over here. So let me calculate that in the next slide. We have to begin with the effective mass 1 upon mu, which is 1 upon mass of electron plus 1 upon mass of proton, and that is equal to me plus mp, me. We can plug in the values, and what we obtain is mu is 9.099 into 10 raised to minus 31 kg. And noting that the mass of the electron is actually 9.1 into 10 to the power minus 31 kg. This is the difference which accounts for a slightly shifted value or estimate for the radiated line. And by how much? So let's find that out numerically. Your h nu is R times hc 1 upon n final square minus 1 upon n initial square, and your delta nu by nu will be delta R by R, because the other quantities will be constants, and within delta R you will have the error associated with delta M alone, because again in R the other quantities such as the charge of the electron or the permittivity, speed of light, Planck's constant are all taken to be constant values. So this is clearly 0.001 upon the mass of electron being 9.1. This is the deviation from the mass of electron if you consider the reduced mass instead of the mass of electron. And that gives us a value about 10 raised to minus 2%. So we can get the value of the shift in the Balmer line based on this correction. That essentially completes this problem, and let's move on to the next one. The emission spectrum associated with the de-excitation of hydrogen atoms is recorded using a grating. For transitions associated with the first line of the Balmer series, a first order maxima is observed at an angle 20 degrees. What is the spacing between the slits of the grating? The question has two parts. In the first part, we just have to find what is the wavelength involved, because this is the first line of the Balmer series. Then this light is incident, and we observe a first order maxima at a certain angle. And then we are required to find what is the spacing between the slits of the grating, which gives us this maxima. So this question is actually trying to combine two concepts, one associated with the quantum physics of the atom and other associated with the optics of the system, where you have electromagnetic radiation incident on a grating and you look at the diffraction produced by the grating. So the first part should be simple. We have Balmer line, so the NF is 2, and your wavelength associated with this line, one indexed with the final comma initial state, will be R times 1 upon 2 square minus 1 upon 3 square, and this will give us 5R upon 36. Okay, let me go to the next slide to continue this problem. So we have 1 upon lambda is 5 upon 36 times r, and we can plug in the value of r here, the Rydberg constant 5 upon 36 into 109,678 centimeter inverse. And what we get is 15233 centimeter inverse, or the wavelength is approximately 6570 angstroms. Let's go to the next slide. Having found this wavelength, you have now this array of holes which form the grating, these openings which form the grating, and we don't know what is the separation D between the gratings, between the openings of the gratings. And we have a screen over here. So let me draw the incident radiation. And this radiation gets deflected at an angle theta, the diffracted ray, because each point is a source of secondary wavelets. So at angle theta, we have to see whether we get constructive interference or not. And one can do that. The expression for the constructive interference is this, where m is an integer, and here it is given to be first order, so m is equal to 1. With this and knowing the lambda, we can find what is the spacing between the slits, for which I shall go to the next slide. So you have D is equal to 6570 into 1, because m is equal to 1, divided by 0.34, which is sine of 20 degrees, and it gives a value 19320 approximately angstroms, or the spacing should be 1.93 micrometers to give us the first order maxima at 20 degrees. Let's go to the next problem. Assume a classical collision between an alpha particle and the gold nucleus. Alpha particles emitted from radium with average velocity of 2 into 10 to the power 7 meter per second are brought to a momentary halt at a distance d from the gold nucleus. If Z is 79 for gold, find the value of d. And we are given the charge of the electron, and we are given the permittivity value of free space. Before we imagine the solution of the problem, I would like to make a comment that this is a very much a classical solution. It's not a quantum mechanical scattering problem, which would be a more exact way of doing this. Nevertheless, we will proceed with this simple version. You have this alpha particle, and this is the nucleus. If it comes very close to the nucleus, it can of course get back deflected. And there is a very small probability, a very small number of alpha particles are back reflected, and this is a very surprising experiment when it was done for the first time by Rutherford. He said that you can imagine it that you are firing cannonballs onto a wall, and some of them just rebound back and come to you, and which is something that usually does not happen in the world around us. But in the quantum world, it does happen. And a very simple classical explanation of this is that here, these alpha particles, they have certain kinetic energy when they start off. And the gold nucleus, there are arrays of gold nucleus if it's a crystal. The gold nucleus are stationary, the gold nuclei are stationary, and their kinetic energy is 0, whereas the potential energy of their interaction between the alpha particle and gold is 0 because they are far away. When the alpha particle comes very close, there is a lot of interaction in terms of the electrostatic interaction between the alpha particle and the gold nucleus. And the kinetic energy is converted to that interaction potential energy. So we will be equating the kinetic energy to the potential energy of electrostatic interaction. The initial kinetic energy is simply mass of the alpha particle times the velocity of the alpha particle square upon 2. And this will be equated to the potential energy, which is the charge of the alpha particle, charge of the gold nucleus, divided by 4 pi epsilon naught d. And our interest actually lies in this quantity called d. We have to find at what t they become equal, because when they become equal, entire kinetic energy has become the potential energy. So let's go to the next slide, and where we will try to find what is d. So from the last expression, d will be equal to 2e into z times e upon 2 pi epsilon naught mv square, and noting that the alpha particle is helium 2 plus, or you can write it as 4 He 2 plus 2. We have put this 2e for the charge and Ze for the gold, and plugging in all the values which are given to us, and noting that the m here will be 4 times the mass of the alpha particle, will be 4 times the mass of proton. Plugging all these values, we will get d equal to 2.8 into 10 raised to minus 14 meters. I leave that as an exercise that you can plug this in and arrive at this answer.